The revision C of the STM32F4 Discovery board is equipped with a new and better accelerometer, LIS3DSH, but no programming example has been provided yet by the producer for this device. We present the simplest possible program for using it for motion detection, as seen in the video. When tilting the board, the corresponding LED is set alight. The program is described briefly in the following. Here is the structure of the project with the added files. Here we present the project options, the microcontroller type, the defined symbols and the preprocessor path, and the setup of the debugger using the ST-Link in serial debugging mode. The program begins with an include directive, some variables definition, the routine for SPI transmit, and the routine for SPI receive. The main part starts with enabling the clock for the peripheral used and continues with the initialization structure for gpio-A, gpio-E, gpio-D, and SPI. Further, we provide the final SPI and accelerometer setup for the simplest operating mode using most of the default parameters, and then we enter an infinite loop where we receive data from the motion sensor and use them for driving the LEDs. First, we shall look in the STM32F4 Discovery User Manual, UM1472. The accelerometer is placed in the midpoint of the 4 user LEDs, and in paragraph 4.8 we find a brief description of its possibilities. We see that it is a U5 integrated circuit in the schematics and is connected via SPI, PA5, PA6 and PA7 for serial clock MISO and MOSI respectively, while chip select uses a pin PE3. Now let's see what is this SPI thing. It stands for Serial Peripheral Interface and is a very popular way for communication between devices, as it needs only a few wires and has a fair enough speed, up to several megabits per second. It uses two shift registers, one contained in the master unit and another contained in the slave. At the ticks of a common clock signal, serial clock, the information is shifted between these registers. So we shall start building the program from scratches using the environment IAR embedded workbench. Go to project, create new project and select C main. We make a new folder, enter it and provide a convenient name for the project. The elementary main block and structure of the project are displayed. I made some resizing of the windows so that the information to be well framed in this video, but they are not mandatory. Now we begin the setup of the project by selecting its options, and first we choose the type of the device. As we use a discovery board, the type is STM32F4 VG. We also click the debugger category, select the driver ST-Link, and in the download tab we check use flash and verify download. We go to category ST-Link and select serial wire debugger SWD. We should try a first compilation here and provide the name of the main file. Now we need some additional source file, so we click project, add files, and go to the libraries, standard peripherals, source, and select first gpio-C, as some ports will be used by the program, then RCC-C for generating the clocks, and next SPI-C as we use the SPI. Now we shall add the path to the included files. We select Libraries, Standard Peripheral Drivers, Include. We also need the path to SEMESYS STM32F4 include for a certain file that we always need, STM32F4 X6.8. We also go to define symbols and type use standard peripheral driver. Now if we try to compile the program, we get an error indicating that the file STM32F4config.h is also needed by some of the other files, so we include in the preprocessor the path to it, STM32F4 Discovery firmware project, firmware upgrade, inc. When we try again to compile, there are no errors, but something more has to be done. We must always add the assembler file startup STM32F4X6.s and the C file system STM32F4XX.c, which deal with the interrupt table and the system's clock. So we add them to the project. We now enter again in the preprocessor and specify their include directory. Libraries, CMCs, ST, STM32, source, templates, IAR. We compile again and assure that there are no errors, so that the project is finally set up and we may begin to write the program. As we mentioned, it is recommendable to use a standard header file STM32F4 X6.h with an include directive. In the main part, we first enable the clock to all GPIOs used. Select the RCC file and inspect its available API functions. We choose the function AHB1 peripheral clock command and copy its prototype. Inspecting the description above this function, we see a list of the possibilities for the first parameter and for the second one. We copy the form of those parameters and paste them in the main file as a reunion for the 3 GPIOs involved. Concerning the SPI clock, as the microcontroller has several SPI channels, we inspect the document STM32F407VG datasheet, and in table 9 alternate functions mapping, we noticed that the involved pins PA5, PA6 and PA7 correspond to SPI1. Now, by inspecting the document STM32F4 Discovery schematics, we notice that SPI1 is connected to the advanced peripheral bus APB2. So we look for the RCC underscore APB2 perif clock command function and copy its prototype. From the brief description above it, we choose the first parameter, RCC underscore APB2 peripheral underscore SPI1, copy and paste it in the main. And for the second parameter, enable. Further, we must build the structures for initialization of the GPIO port following a standard procedure. As we've seen, the accelerometer uses some pins from GPIO A and GPIO E. We open the GPIO source file and choose the gpio init function. We copy its prototype and start building the structure. For the first parameter, we choose gpio-a, and from the brief description we see that gpio init struct is a pointer to a gpio init type def, so we copy the syntax in a new line before invoking the function and define the structure by simply deleting the asterisk sign. For the second, we keep only gpio init struct and place an and sign in front of it to denote a pointer. Now we copy the name of the structure after the definition and dereference it by placing a point at the end. The editor should display a drop box with the members of the structure. We choose gpio pin. Now right click on gpio init type def, go to definition of gpio init type def, which send us in the associated header file at the description of the structure's members. By scrolling up we may see their definitions, but the syntax for the pin is obtained immediately by scrolling down. We use pin 5, so we copy its definition to main and reunite this with similar definitions for pin 6 and 7. Then we copy again the structure, dereference it, and choose the member gpio mode. Again, following the described standard procedure, right click on gpio init type def and choose the go to definition of gpio init type def, which send us in the associated header file, and from its description we right click on the gpio mode type def. From the type def enumeration we choose the syntax for the alternate function mode, as this is the case for SPI assignment of this pin. The referencing against the structure, we choose output type, which is mandatory push-pull, otherwise it could affect the ST-Link communication. The syntax is found by right-clicking on the gpio mode type def, then clicking go to definition of gpio type def and choosing from the corresponding type def enumeration gpio underscore pp. We copy this in the main. A similar structure is necessary for gpio-e, which provides the chip select command for the accelerometer on pin 3. So we copy and modify this structure by specifying pin 3, the out mode following the described standard procedure, and also specifying the E port. As port A is used with some alternate functions, we must specify their assignment. For this, we search the API functions for GPIO and take the GPIO pin AF config 1. We copy its prototype in main and choose the parameters. The first one is obviously GPIO-A. And for the second one, from the brief description above the prototype definition, we copy the syntax for the pin source. Finally, we choose and copy gpio AF SPI for the third parameter. We copy this function twice and modify it for pin 6 and pin 7 respectively. Now we have to deal with the SPI structure initialization. We open the SPI source file and from the AP functions we choose SPI init. We copy the prototype in main and start building the initialization structure following the standard procedure. The first parameter is obviously SPI1. And as described in the brief above the prototype in source file, the second one is a pointer to a SPI init structure. So we copy these expressions from the prototype and put them on a new line, and we delete the asterisk sign. We adjust the second parameter for indicating that it is a pointer by placing an and sign before it. Now we start to dereference the SPI init struct and set up its members. members. First we choose the SPI baud rate prescaler. Following the standard procedure, we find the definition group for SPI baud rate prescaler, and we copy and paste in main the lower value which corresponds to the maximum speed for SPI. Again, copy the structure name on a new line, dereference it, and choose direction. Then find the definition group by searching SPI data direction mentioned in the member's description, and copy-paste in main the 2 lines full duplex alternative. The next member is the mode, and following a similar way, we choose the master mode. Now we have to choose a data size member by dereferencing the structure name as usual. For this member and the rest of them, we must inspect the datasheet of the LIS3DSH accelerometer. In paragraph 5.2, we see the waveforms of the serial interface. We notice that on the input SDI, the device first receives 8 bits containing an address and the 8 bits containing data. On the output SDO, it responds with 8 data bits also. So, after looking for the definition group SPI data size mentioned in the description of this member, we choose SPI data size 8B. The next member will specify the significance of the first bit. From the waveforms diagram, we may see that the first bit is always the most significant bit, so we choose the option SPI first bit M is B and copy it in main. For the SPI CPOL and SPI CPHA members, we read the specification for SDI and SDO lines in the documentation. They are captured at the rising edge of the SPC and they are driven by the falling one. Thus, looking for the definition group referring to the polarity of the clock, we choose and copy SPI CPOL underscore high. Also, we choose for the member SPI CPHA referring to the phase of the clock as the active edge, SPI CPHA 2 edge. For the final member of the SPI structure, we have to read carefully the SPI register's description in the reference manual of the microcontroller. Here, in the description of SPI control register 1, we may see that bit 9 enables the software slave management if it is set. When set, the NSS pin, which is a slave select pin, is replaced with the value of the SSI bit. Hence, both the bits must be set, so that we specify SPI NS soft reunited with SPI NSS internal soft set. The last specification is found after several searches for NSS in the SPI header file. As may be seen in the time diagram, the idle state has a 1 on this line, which is connected to the PE3 pin. So in the initial state, this pin must be in 1, and so we go to the gpio source file and select the API function gpio set bits and copy its prototype in main file. The first parameter is obviously gpio, and the second is taken from the brief above the prototype. We copy the syntax and modify it for specifying pin 3 in main file. Now we have to start the SPI. From the SPI source file, we select the prototype for the API function SPI command and copy it in main. With the first parameter SPI1, and the second one enable. Let's try a new compilation and assure that there are no errors. The final part, the initialization process, must send to the accelerometer the desired parameters for its 58 registers. We may leave most of them in the default state, but it is mandatory to send a certain command to the control register 4, as we shall see. We may replace the return statement with an infinite loop while void for the moment, which will contain the transmit and receive blocks and those using the data from the accelerometer. As some of these blocks are repeated several times, we will write them as routines before the main loop. First, we will write the transmission routine, which needs two parameters. The address of the envisaged register and the corresponding data, both of them being 8 bits unsigned integers. At the beginning of the cycle, we must put the CS line in 0, which requests a gpio reset by function. We copy its prototype from the gpio source file and put the first parameter gpio and the second one gpio pin 3. Now, for checking that no other transmission is in execution, we select from the SPI source file the function SPI I to S gets status flag. The first parameter is SPI 1 and the second one is SPI I to S TXE flag, chosen from the brief description above the prototype. While this flag is not set, it means that another transmission is in progress and the microcontroller should do nothing. After that, it becomes set and we may begin the current transmission. For that, we select from the SPI source file the function SPI I to S end data and copy its prototype in main file. The first parameter is obviously SPI1 and the second one, according to the datasheet, must be the address of the desired register. Whenever something is sent, something else is received, so that we must read the data register to complete this phase. For that, we invoke again the function SPI I to S get status flag, taking the first parameter SPI1 and choosing for the second parameter the SPI I to S RxNE flag from the brief description above the prototype. This flag denotes that the receive register is not empty, and while it is not set, it means that the reception is still in progress and the processor should do nothing. After that, the data register should be read using the function SPI I to S receive data, having the parameter SPI1, which concludes the cycle for 1 byte, the address. For sending data, the cycle is the same, so we copy these 4 lines and paste them with the parameter data instead of address. Finally, according to the diagram, we have to write the CS line in 1, so we copy the first statement of the routine and paste it at the end, but with the function gpio set bytes. The receive routine is in the most part identical, so we copy the transmission one and make some modifications. First, we modify the name, then we keep a single argument, the address, and the received data is the returned unsigned 8-bit integer result. From the time diagram, we may notice that the first bit of the address must be 0 for transmission and 1 for reception. So, at the beginning of the cycle, we must set this bit in 1 by making a NOR of the address with the hexadecimal constant 80. The cycle follows the same procedure, but in the data sending phase, we may use a dummy byte to ensure the reception. We verify that there are no errors at the compilation and start to use these routines. The register description in the datasheet of the accelerometer reveals that the bit combination in control register 4 at restart corresponds to the power down mode, so we must send another combination to this register at the address 20 hexadecimal. Choosing output data rate bits ODR3 to ODR0 as 0110, which means also 100 Hz, and keeping in 1 the bits X, Y, and Z enable, we must send the hexadecimal 6 7 to this address. Now we finally may read data from the accelerometer by invoking the receive routine and placing the result in a signed 8-bit integer that we define at the beginning. We choose the address of the high byte of the X register, hexadecimal to 9. We compile the program, load it in the flash, and then from the View tag we open a live watch window. We enter the variable holding the data from the accelerometer and adjust it in a signed decimal form. Now we start the program and notice the values of the variable when inclining the board in a sense and another. As an example for using the data, we will display the information received from the accelerometer on the user LEDs. The Discovery board schematics shows that they are placed on the 4 upper pins of gpio, so we have to provide clock for this port also. We shall initialize this port in a similar way output as gpio, so we copy this block and paste it with the proper name of the port and the corresponding reunion of pins. In the infinite loop, we test if the value of x is under -20, and if so, the green LED will be on, otherwise it will be off. Also, if x is above 20, the red LED will be on, otherwise it will be off. We compile the program, load it in the flash, and run. We may notice that indeed, when we incline the board one way or another, the corresponding LEDs become on or off. We may also use the y-axis of the accelerometer for driving the other LEDs. From the datasheet, we learn that the address of the higher byte of the Y register is hexadecimal 2B. So we will define a new signed 8-bit integer variable Y, and we will read it from the higher Y register. Then we copy the LED control instructions and paste them with the modified variable and port pin. Finally, we compile the program, load it in the flash memory, and run it. We may notice that indeed, when we incline the board in any direction, the corresponding LEDs, single or in pairs, become on or off. As an example for changing other parameters of the accelerometer, at the end of the initialization part, we insert another transmission command by copying and modifying the existing one. Looking in the documentation, we may change, for example, the anti-aliasing filter bandwidth and the full scale, which are specified in control register 5. Choosing 200 Hz and plus minus 4G, we must write at the register's address 24 hexadecimal the byte 0100 1000, which means 8 in hexadecimal. Now, if we compile, flash and run the program, we notice, as it was expected, that the board has to be inclined at a bigger angle to turn on the corresponding LEDs, because the default full scale was plus minus 2G. The program is fairly simple, as it uses polling for detecting the end of any transaction with the accelerometer, which is suitable for most of the applications. As an exercise, you may try to modify it by activating the interrupts to spare a couple of microseconds wasted in polling, following the examples given in my previous tutorials.